Sandeep Singh, and I will be going to talk about the quantum internet, its architecture and challenges. And second part would be quantum network topologies and protocols. So both of the things will be, interlinked. So, so I will kind of wherever there will be, you know, network topology discussion, it will be integrated with the quantum internet. Okay, so the agenda of this talk is I will introduce the quantum internet and give you the overview, also provide some motivation why we need quantum internet. In the first part, we will discuss about what is the quantum internet, how we can develop it through the layered architecture, and what is the current scenario, what are different test beds, and what different challenges we have today. And in the second part, we will have the quantum network topology, quantum network protocols, and if time permits, I will talk about some of my past and current research. Okay, and during the talk, whenever you have any questions, you can ask in the chat. I will try to answer during the talk itself instead of waiting at the end. And let's make a little bit interactive, but I think you will not be able to ask questions but by voice, but you can write in the chat. So what is quantum internet? I mean, before understanding the quantum internet, we need to understand what is internet, right? So I think some of you already know what is internet. So basically it is interconnecting network, right? So network connecting quantum computers instead of the normal, let's say the computers would, or nodes to transfer the quantum information would define the quantum internet instead of the connecting the classical computer and transferring the classical bits, right? So that's the main fundamental difference that you should take away from this lecture. So quantum internet transfers the quantum information and it interconnects the quantum computer or computers or quantum nodes. Right. And why do we need it? Why? I mean, what is the motivation behind it? So there are many applications that are out of reach of today's, classical internet, which is TCP over IP. And for example, the secure communication. Today's internet does not provide the secure communication, which is information theoretic, provable. And the second application would be powerful distributed computing. And yes, somehow this full slide is not working still. Okay. And the third application is advanced sensing and metrology, right? So we have different applications. And if we want to do distributed computing, then meaning that you need to run the algorithms on distributed quantum computers, then you need to interconnect them, right? And then also comes the providing the secure communication. And when you interconnect them, you can also do some advanced sensing or metrology. So interconnecting different quantum computers, or you can use it for the quantum cryptography, that is for secure communication. And here is the main role of quantum networking or quantum internet, right? So that's the fundamental thing that you should take it from this talk, right? So the question is why quantum networking or in quantum internet, right? So in general, if you look at internet distributes bits, classical internet, right? On the other hand, quantum internet will distribute the quantum bits. In short, we call it qubits, between different locations for various applications, right? As we discussed in the previous slide. Today's internet have several challenges. For example, if you look at the transport control protocol over internet protocol, right? So protocol APSCHE, which is 4-layered, which we will see in the coming slides, it provides the best effort services, meaning that it cannot guarantee you that within, let's say, few milliseconds or seconds that your data will reach to the destination, right? It will provide the best effort, that based on the network, congestion, etc. The type packet or data will take its own time, right, to reach the destination. And also scalability is a problem. Data security is another big problem in classical internet. We use the classical encryption and decryption algorithm. And if you look at how the data is transferred, so basically a single bit or few bits consisting of a, let's say, symbol. To transfer them, we need few thousands of photons, or let's say few, because each bit, if you take one zero, right, that will have some power level, and that will be thousands of photons for transferring a few bit, right? On the Okay, I will talk about quantum internet, how it is different. But let's say another problem. So information rate per bit, right, per photon, right? So if you use the thousands of photons to transfer single bit of information, then obviously your information rate reduces, right? And also it is slow. You cannot run many advanced, biological or some advanced models with the quantum internet, right? Quantum compute with the classical computers, right? So we need quantum computers, and we need to interconnect them for distributed computing and other applications. So now, how does this quantum internet help? So quantum internet has some few features which is unique, for example, called superposition and entanglement. And I will come to these topics in a few minutes. And because of this, there is one more theorem called no cloning theorem, which says that you cannot copy the quantum state. It provides the information theoretic, security. And now, why it's energy efficient, or someone still debates whether it's there or not, because of various reasons. You can use a single photon or single particle to transfer the information, right? So it may be energy efficient, but it's a little bit debatable, because you need to cool down the detector, which requires energy and all. So that's a separate issue. And also because of this superposition and entanglement, so it provides us exponentially speed up in computing. So these are some of the benefits of quantum internet. And the goal is to build the local area networks, metropolitan area network, wide area networks. And once we have them, we can interconnect them to build the global quantum internet, right? So that's the fundamental thing that we want to do. I already spoke about some applications. So typically this quantum computing and the quantum networking and security are the two main, apart from the sensing. But if you look at recent development, so quantum key distribution is kind of now you can buy a product, and which is very good, though it took more than 45 years to develop it, since the first BB84 quantum key distribution protocol came into the existence. But yeah, this technology is took time, but yeah, it's very promising. Another would be this secure communication, and which will require the quantum internet, and which has to be secure, right? And the enhanced sensing it can provide, because it's the single photon based or single particle based. So and also some other properties make it very sensitive. Some sensitive information we can gather. And yeah, so apart from these, some of these applications for quantum computing and networking, so there are some open applications, such as machine learning, quantum machine learning, I would say, or some how do we use it in chemistry or materials, to find structure, or you can make some for vaccine also, one can use the high processing capability of quantum computers. Yeah, so these are open, but yeah, these are very important. And I see the question sensing. Yes, sensing is very important. So quantum provides the enhanced sensing capability compared to the classical sensing. Classical sensing means the way we do we do the classical communication. So I already explained how I'm going to explain it, how the classical communication and quantum communication differs, and how you can use it for sensing application also. And there is another class of applications for sensing, which is the diamond based or something. So that's a separate issue. But how can we use communication for sensing? That's a different thing. That is what I will be talking. Okay, so um, yeah, so but you see that in around 2000, this artificial intelligence was a boom, because a lot of money was invested by NVIDIA and many other companies in 2000, around 2010. Quantum computing in general, or other fields of quantum, I mean, got a huge amount of money, so government sponsored projects were established, or industry got huge money, and Google already demonstrated, the quantum computing feature, and there are many different companies that got huge amount of money, and money is required, yes, for developing novel, systems. And one is the Quantum in the US, which received billions of dollars, and they are working on the silicon photonics based quantum computers. And the current challenges, I mean, I will talk, but in short, I can say this scalability is the main issue, and of course the how to correct the errors. Those are things. But flooding of the this capital venture money, so that is good, but it also take us to the unreal promises of quantum computing. Still, people debate whether it's real, whether it's whether it will be it will be coming to the market. When I say it will be coming to the market, meaning that the few thousands of qubits, or we need to if to process to do some applications. And if I give you a number, we need millions of qubits to break the RSA encryption in a day or two. So that's huge. Where are we today? We are at the few hundreds qubit processor, right, limit. So we need to go a long way, but but this is how the great technology is developed. We need to continuously work, and of course, money is not all. We need to work together and see we can push the limit of the technology. Yeah. So now coming to the evolution of technology, this for it all started, I would say, for networking applications, started in 1940s, right? So developing from the vacuum tube, transistor, integrated circuit chips, and personal computer in 1980s by Macintosh, right? So this led the initial development of the, I would say, the networking. And second round of development started in 1970s with the as I said, transport control protocol over IP, meaning that some protocols and algorithms were developed on top of the deployed, hardware or the networks. In the 1960s, there was few, 5-6 nodes, this ARPANET, and that enabled the classical, basically, network to interconnect them. The quantum, the classical computers, which are located in different cities, as you can see here. And let me see if I can make the pointer now. So because of full slide is not coming, I'm not sure why. Okay, but you can see my cursor. Yeah. So first round of development was related to the hardware, and the second round was the protocols and algorithms, starting from the TCP/IP, Ethernet, Internet, World Wide Web, and then Google came, and it also transformed the internet, actually, the way we search is still today. And around 2010, this big data or AI, boom came. So around 2010, the question was, what next, right? That's a kind of very important question. And yeah, okay, so yeah, so that time. The question was what next, and it was the quantum related development. So in the beginning, so we saw the development of quantum hardware, from processors, memory. Still, we don't have the memory which can be used in the field, but yeah, there are different the technology that were developed. And even in 2025, this Majorana, this topological qubit chip developed by Microsoft, it also it also led the technology to the next level. So again, similar to the what previous round of the revolution in networking came. So here, after developing the quantum computer related hardware, what we need is to, how do we interconnect them, right? That's the question. And this will also enable this quantum key distribution, which I will talk a little bit. Yeah, one question is in 2007 D wave, this 1000 qubit came. Yeah, I need to check. Most likely, you may be. I mean, I don't know whether it's 2015 or 2007. I need to double check. Okay. Okay, so this development was initially questioned by many actually. You see, the early days in 1900s, famous physicists like Albert Einstein, he told, I mean, he questioned actually the quantum postulates that is proposed by the Copenhagen Summit, uh, founded, I mean, or initiated by the Niels Bohr and some of his colleagues. And in fact, Richard Feynman, which was the one of the best physicists during his time, he even told that if you think that you understand quantum mechanics, then you don't understand quantum. It's still valid today because some of the postulates are still debatable. But there have been development, and we saw in 2022, the Nobel Prize was given to three physicists: Alan Aspect, John F. Clauser, and Anton Zeilinger for developing various things in quantum domain. For example, Alan Aspect worked on the experiments with entangled photons. Clauser worked on establishing the violation of Bell inequalities, and Zeilinger, he is a pioneer in quantum information and quantum information science. Not only that, but in 2025, last year, right? Another three, physicists won the Nobel Prize in quantum domain, basically for quantum tunneling, right? You can look at more in details. So, though there have been some open questions, there have been development, and this is actually encouraging for us to work in this domain and continue to develop the technology. So now I will talk about the little basics. I have now until now I gave you some motivation. Why do we need quantum internet? Why do we need quantum computers? All. Let's try to understand what is the difference between the classical communication versus the quantum communication, right? So if you take any classical system, right? We transfer the bits, binary digits. In short, we call it a bit, which is represented as typically, let's say, on state as 1 and off state as 0, right? And the sorry, the system must be in the state of 1 or 0. You need to understand or, right? On the other hand, in quantum system, we register or we transfer as qubit, right? And for if we take an example of an atom, so an atom can be, or a particle can be in the ground state, we can say as 0, but Dirac gave a special notation of get 0, this symbol that you see here, or and excited state we represent as 1, right? Get 1. Right. If we take the photon example, we can use one of the properties of photon, which is polarization, and we can say that that if it is horizontal polarization, then let's say state 0. This is just the nomenclature you can interchange as get 0, and the vertical polarization as state 1, right? Get 1, right? So you can in terms of linear algebra, it's all about the linear algebra, So this horizontal polarized state or photon state we can represent as the get h as state 0, which you can write as the column vector 1 0 as a basis, and the vertical polarized state as 1, and we can represent it as a 0 1, right? These will be forming the basis of the simple qubit, right? Qubit, right? Two particle system, we can say. Right. So, but here, what is the difference between the classical system and the quantum? The system here in quantum can be in the superposition state. This is the most important thing to know, and I think many of you must be knowing. So, quantum state psi can be written as a linear combination of state 0 plus state 1 and with the scaling factor, right? And the scaling factor is governed by mod for here alpha and beta. So mod alpha square plus mod beta square as 1, because this will also define the probability that you will see. And these were the initial, the development of superposition. And Heisenberg and Schrodinger and Einstein, they had many communications. And when, the I think one of these Schrodinger or Heisenberg, they proposed this idea of a cat as whether a cat is dead or alive, at the same time. Right. So until we see the system, we don't know, and we can say that it is in the superposed state. This is just the, the for understanding. And yeah. And if we take this further discussion further, how it is different, let's take a classical, let's say, register, which has you have the let's say here we have the 4 bits you want to you want to transmit from Alice to Bob. You can transmit it error-free as long as your data rate is below the channel capacity. That is channel capacity, right? Also coming from the channel capacity theorem, right? But the question is, how do we transfer this quantum bit, or let's say state psi, from Alice to Bob? Because how do we transfer from one node to another node? Because it has conflict with the quantum mechanics, right? First conflict is the no cloning theorem. It says that it is impossible to duplicate an unknown quantum state. And the second is Heisenberg uncertainty principle, that it is impossible to know a quantum state. So these two theorems makes our life difficult to operate with the quantum bits, right? Or qubits. So how do we bypass, or I would say, to work with these laws? We will see in the coming slides. But these are the these theorems also enable this quantum, quantum, how do you say, quantum security, actually, right? Especially the no cloning theorem and the Heisenberg uncertainty principle. So yeah. Now let's look at the superposition and entanglement. So first, the superposition of qubits. How do we say what is superposition? So we can understand with a simple example. Let's say a few string of bits. We can say that this exists in a superposed state of various all combination of the string of zeros and ones with certain probability, right? Particles can exist in multiple states at the same time, known as superposition, right? And this superposition leads to uncertainty. Until we measure, we don't know in which state the quantum system is, right? So that's the superposition, right? And what is entanglement? So let's look at one like the simple result. In two classical systems, we say that the bit 1 and bit 2 are statistically dependent if the joint probability is not equal to the individual factor of individual probability, right? Then they are dependent. If it's equal, then they are independent, right? That's the coming from the probability theory, right? And we say that two quantum systems can be entangled if you cannot factorize the quantum state. When we say entanglement, it's always the minimum is the two particle. It can be more than two particles also, right? So we cannot factorize the joint state as the product of the individual state, right? So that's the factor. And what you see, the state here is called one of the Bell states. And there are 4 Bell states. I will tell you later also the Bell state, why it's so famous. And what does it tell you? It tells you that it's two particle system. So state, state, first particle is in state 0 at the same time the second particle is in state 1. Or if the first particle is in state 1, then second particle is in state 0, right? This is the basically the factor for the probability. And and so to give you the intuition why it's so powerful, right? So yeah, Heisenberg gave this the cat example, but in general, if you look at basically this is as entanglement as a strange correlation, right? We know the state of the system as a whole, not the individual pieces, right? And let's take another example of what benefits it brings or why is it powerful. So let's say atom is in the cold state, right, or ground state, and it emits a photon in the left channel. Or an atom is in hot state or excited state, and it emits a photon in the right channel, right? And if we put a photodetector here and photodetector here, far away, if we measure that that photon, you detect that the photon has arrived in the left channel immediately without measuring the quantum, the atom. You know that this atom is in cold state, right? That's the entanglement, right? If you measure one, you know the state of the other. So atom state and the photon state are entangled, right? So that benefit is big. So even though the particles they're entangled and you send it thousands of kilometers, providing all the ideal conditions, then if you measure one, you know the state of the others, and this is what the Einstein question, the question that information cannot be propagated more than the speed of the light, right? Which I mean, which is not. I mean, it's not that information is propagating more than the speed of the light, but because there will be there we need the confirmation. We need the classical communication channel also to confirm it. So. So yeah, so that was the initial kind of the struggle that many physicists had to understand these basically postulates and the properties. But as I told you, some of the physicists, they already developed the single photon entangled photon source, entangled photon single photon detectors, and they demonstrated its entanglement, through different criteria. Okay, so as I told you little before, let me drink. Yeah. So the transferring, basically the role of the quantum networks is to transfer the quantum information. In short, we call it qubits, right? In quantum domain, we encode the information on the single photon. In classical, we have a pulse of light, which is few, let's say, milliwatt, and that carries a few bits of information, bits on the modulation technique, right? And that's the fundamental difference. And yeah, sorry. Yeah. So what enables this the quantum network, the security. So this is the no cloning theorem that I little bit sorry. I explained to you that it tells that you cannot copy an individual and an unknown, an arbitrary quantum state. If you don't know how it is generated, you cannot copy it at any other intermediate node. That is what currently that is what that's the bottleneck. But also it provides the security. Without this, we will not have the information theoretic security. But the question is, it also makes us in trouble that how do we transfer the qubits, right? And that is solved by teleportation, quantum teleportation protocol, this one. So I will explain to you about the teleportation in the coming slides, but it enables basically the the transferring it of quantum bits from one node to any other node, right? Though there are, on paper, there have been some quantum teleportation protocols, but also some, the labs have demonstrated it, but still you cannot buy any product or chip level teleportation. That and use it in the network. Still, work has been going on, and yeah, around the world, yeah, it's many physicists are working on it. The one of the another the another challenge is the as you see here, the quantum information is a single photon. You cannot amplify it. How does the amplification work? So if in short, basically, I'm not sure if I can draw here. So you have, let's say, you take laser light, you and send it, encode some information and send it over few kilometers. Due to the loss in the fiber or free space, the number of photons per bit reduces, right? It gets lost, right? It gets absorbed, right? Scattered. There are many loss mechanisms, right? And so we need to amplify it, right? So what we do, we use the amplifier, right? Whether it's erbium doped fiber amplifier or any some semiconductor optical amplifier. So what it does, it basically uses some external sources, pumps, which converts some form of energy into another form of energy, meaning that let's say you have, after you transmit 1,000 photons, after few kilometers, it reduced to, let's say, let's say 500, right? You can compute after how many distance it can be. If the attenuation or loss is 0 point, let's say 2 or 0.3 dB per kilometer, you can compute how many kilometers, after how many kilometers you will lose half of the power, right? Right. So how do we then amplify it? We typically use the EDFA, and it uses the external pump, and it will from it will add basically additional photons with the same phase and frequency, and for that bit. So basically it adds number of photons, right? So that you have the same power. There are more things involved, but let's not go into that now. On the other hand, this is very, like that problematic in quantum. How will you amplify the single photon? So still we are struggling with this, and there is no solution. So long distance communication, quantum communication is limited by this, right? Now, I would like to bring, like, once you have the, let's say you want to build a quantum network, how will you build? You have quantum computers, you want to interconnect them, right? So there are various, the topology that you can use, network topology. For example, you can use linear chain or tree based topology, or a star topology, ring topology, mesh topology, or a fully connected topology, right? Basically connecting them through the fiber or free space, right, to these, let's say, quantum nodes or quantum computers, right? And different has different, the positives and negatives. And if we go further into the details, typically how the classical network is built, right? So we have basically local area network that interconnects within the buildings, right? And then we interconnect these local area networks with the metropolitan area network within the cities, right? And these metropolitan area networks are interconnected through the wide area network WAN, through that interconnects through the the subsea and intercontinent, right? This is how the global internet is built up, right? And this is the fundamental, or the thing for the quantum, or in general internet, right? So how to build an internet, right? And quantum internet basically will be the similar principle, but it will transfer the quantum bits of information instead of classical bits of information. There are coexistence network, meaning that you can transfer classical on one channel and quantum on another channel. But let's simplify it and keep it just for the quantum, in transferring the quantum bits of information for the quantum internet, right? And obviously, there are many different options for each local area network and metropolitan area network, or the wide area network. One typical, like you can either interconnect through the fiber, or you can use if you are dealing with the photons, right, or the optical thing. You can also use some other, there are many different groups. They are working on uh, different types of qubits, superconducting, or there are different. So they will then we may need different types of channels, or we need the conversion, or different transducers which converts the the electrons to the photons and so on. Okay, so but the typical the network that we will need is the fiber optical network, because it has the low loss, and that's the main thing, and it will enable the global quantum internet, right? Okay, so typically, if you look at the on metropolitan area network, it's typically in the ring yeah, in the ring structure. Local area network is the typically LAN what you have seen, and also through this metropolitan area network, you can have the passive optical network, meaning that you have one central node as a splitter or combiner, and you send the signal, and it will simply split the power. That's the simplest thing, and you can interconnect even the this base stations, right? And with this, the rings, you can have multiple rings, and you can connect them with the with the wide area network, and we can connect this through the submarine cables. And yeah, this will enable the global internet, but there is also an option with connecting these nodes with the the satellite or the free space communication or satellite communication, right? So they can that can also enable the long distance quantum communication, right? Yeah. So that's the typical network topology that is being used today. And you might have heard about the Starlink, and there are many other companies that are having many thousands of satellites in low Earth orbit. Still, they are not providing the quantum, the communication, but the typical classical communication they do. But China has already demonstrated the quantum communication over the satellite, right, to enable the, the quantum communication for the long distance, right? Okay. So what are the different components for the quantum internet, right? So we have you have the personal computers, right? We want to connect it with the internet, right? So you connect it with the access point, and then we need a router, right? Can be connected through different, the repeaters and multiple repeaters, and you can go and connect from one local area network to metropolitan area network to the other local area network, and interconnecting different cities, and different cities will be interconnected with the global internet through the POP that is present, or landing stations at the submarine cables, where, for example, in Mumbai or Chennai or some cities they have it. Okay, so and another way is the satellite based, right? So we need the ground stations for that, right? So this is another way to interconnect them. These are different topology that or the architecture that people are using for the classical network, and also it can be used for the quantum network, but we need the quantum devices for that, right? So what have been demonstrated so far? Have been many different work that has been done, but I have here listed two main. One is in the Chicago, which has few nodes over 200 kilometers network, and Argonne National Laboratory and University of Chicago connecting to another Illinois, the node, and they have demonstrated the coexistence of the classical and the quantum, communication over the same fiber, and sending also the classical internet traffic. Recently, last year, the famous paper from Professor Prem Kumar came in. Right, and another is the in the bigger network is in the China, which is 4,000. Now it's must be have been crossed to 5,000, more than 5,000, but it's a little old to 2021 data. So it has many nodes, right? And some of the nodes we call it trusted nodes, right? Where we how do you say, where we transfer the quantum information to the classical, again, again changing it to the quantum, right? We call it trusted node. But there are network which will be trust free, right? Meaning that we don't have to change the information from the quantum to the classical. And I will talk with you shortly. Okay, so in India, where are we? So Space Application Center in Ahmedabad, they have demonstrated the quantum communication link over 300 meters between two different buildings, and they demonstrated the BBM90. This is one of the famous entanglement based quantum key distribution protocol, and yeah, which is capable of providing the secure keys for various applications, right? So basically, quantum key distribution main role is to securely generate and distribute the keys that can be later used for encryption of the data or decryption of the data, right? There is another network that will be coming up. from Delhi to Roorkee, and this will be around 300 kilometers. And here, the nodes that we are also part in this project, and the nodes are basically called the trusted free, right? So trusted free means that you cannot basically for long distance. It's a big issue. And how do we enable it? One way is the satellite through the satellite, right? Where we have satellite as a as a, let's say, the one node or Alice which distributes the entangled photon sources to, for example, if we have another node here, so it will distribute the entangled photons to this node and enable the quantum key distribution protocol, right? So BBM92 is one of the example, or there are many, E91. There are many different entanglement-based protocols. There is another category of quantum key distribution protocol, which is, for example, the prepare and measure. And maybe I will not go into that, but yeah, you can take a look. So different links have different distances, and we are trying to develop and demonstrate different, the protocols, but not just the QKD, but also some networking features with also development of the, the chip-based source. And, so there are many different things that will be developed over the years, right? So yeah, that's it. And another which I've not listed is with IIT Madras, and they will be deploying this network from Chennai to Bangalore. And but in their case, it's the QKT mostly, but with we call it continuous variable QKT, meaning that no entanglement distribution, right? Not the protocols that is not related to the entanglement, right? Simple prepare and measure based CVQKT. Okay, so that's the difference between these two networks, and yeah, we are looking forward to it. If you have questions, please let me know. Okay, so yeah, so maybe we will have break in few minutes. Maybe I will take a break now itself. It's 11. Okay, here it's 11:17, but 10 minutes of break, and then we will continue at 11:30. Rajendra, is that okay? Okay, there are some questions I can answer before we go for a break. Are there active quantum entanglement networks in India? No. Short answer is no, because entanglement-based network requires this, superconducting nanowire single photon detectors, SNSPDs, which is very expensive. I think between in the lab, there have been some demonstration, but there is no deployed network in India yet. So that's and which one network that I was showing you, this that this one 6 nodes, and in fact we will be having one more node here because the distance is too much. So we will have another node here. So 7, yeah, 7 node network. So basically this is all entanglement based network. This is the free space link, this is the fiber optical links, and this will be the first of its kind in India. Yeah. And another question is, are there any types of quantum communications we can use in microgrids or renewable energy application? Okay, that's very interesting. I don't have answer to that right now. Microgrids, maybe I will think about it in the break. And maybe some of you also can look over internet. There must be, because this quantum communication or networking or yeah, computing is covering all different domains. So maybe some expert in microgrids or renewable energy can answer it better, which has little more, little bit knowledge of the quantum domain. But I will take a look. Okay, so that's the key thing that we want to do the entanglement based, which is very fascinating. On the other, without entanglement, as compared to without entanglement. So yeah, so that's it. So let's take a 10-minute break, and let's meet at 11:30 here. Means what time will be? It's 1 hour, so 4 o'clock, right? Yeah, 4 o'clock. Okay.
Yes, sir, at 4 o'clock.
Yeah. So let's meet at 4 o'clock. Is it okay?
Yes, sir, sure.
Okay, good, good. Okay, so you can type some of the questions, and I will take a look and answer after the short break. Thank you. Thank you so much.
Is there any issue, sir, regarding? Because your slide is not showing and your voice is not audible. Excuse me, sir, you are not audible. Your screen is clear, but you are not audible, sir. Hello, excuse me, sir, you are not audible. Kindly unmute your mic because we are not able to hear you. Hello, can you hear us, sir? You are not audible. Dear participants, maybe there is a technical issue, so the sir will disconnect and resume the session within minutes. Now you are audible, sir. Clear. Voice is clear.
Okay, I'm so sorry for this disruption. I had to change room because somehow with multiple monitors, I could not share the full screen. So okay, good. So let's quickly
Not
go
an
to
issue,
the,
sir.
go to the slide. Okay, so what I was saying, I need to do once again, laser pointer on, and let me put it away. So yes, I was talking about different opportunities that quantum internet, presents. For example, we need to develop different quantum devices from processor, memory, etc. And we need to develop protocols, algorithms, simulation models. Then we need to develop entanglement distribution for long distance, quantum teleportation. And one very important thing is the quantum error correction. Like we have the classical error correction, we need to develop the quantum error correction, the codes and the methodology, which is really impacting the development of the quantum communication and because of the noise, quantum noise. And yeah, okay. So, I mean, the quantum internet is is good, but it presents big challenges. So everything is a challenge, right? We need to maintain the coherence over long distances. This is the one of the biggest challenge in the quantum communication, right? Whether it's a fiber network or the free space network, and when you work with the different wavelengths of frequency and synchronize many users, this coherence of the particles, it will, as it propagates, it lose its quantum properties over the distances, and to maintain that, it's a big issue. And quantum internet hardware we need to develop. I was saying about that quantum processor, for example, quantum memory with optical interface, right? And we need high speed, low loss, the switches, repeaters, What is a repeater? I will explain, in short, in short a while. Okay, and we need to have improved quantum entanglement or non-entanglement sources and the detectors, right? Then it will enable the global scale quantum, the internet. Okay, now coming to the classical versus the quantum internet protocol stack. So I think some of you may know about the open system interconnect protocol stack. It has the 7 layers, but in TCP IP stack it has been reduced to 5 layers. An application layer includes the first 3 or top 3 layers functionality. But so typically we and in fact you can call it, let's say, 4 layer. Basically link layer has consume this physical layer functionality in terms of Ethernet, for example. So basically the role, similar to the classical internet protocol stack, we need to develop the quantum internet protocol stack. So what is the role of classical internet this protocol stack? In application layer, we have applications, right, running, right? And then we want to basically it's internet, we want to transfer the data, right? So we establish basically reliable or unreliable secure communication, secure communication. And how do? We do it with the transport layer, right? And there it comes the TCP or UDP. UDP is the user datagram protocol, and TCP is the transport layer control protocol, which establishes the sessions, and then the transmission of data can be possible, right? And the network layer deals with the intermediate nodes. How when a new, let's say, data chunks, which we can call it packets, comes, then how do we switch and route, right? So that will be the job of the network layer. And the link layer is between the one node to another node. How do you transfer particular data rate from the direct over the direct link, right? That will be the job of link layer. And the physical layer deals with the formats data. How do you transfer the data on the wire, right? Similar to that, we need to develop the quantum internet protocol stack. Basically we need to have quantum applications, right, running, and transport. When we say transport, it can be over the classical coexistence network, or we can have a dark fiber or the quantum networks. And the network layer will deal with the entanglement distribution, and link layer will be how do you transfer the quantum data over the link, basically transduction or through the superconducting or photonic qubits, right? And physical layer will be involved with the hardware, right? Quantum hardware that is involved in the data qubits generation and the transfer. Yeah, so you can read this survey of quantum internet protocols from a layered perspective. It's published in IEEE Communication Survey and Tutorial 2024. It's not that the old, and it has very good detailed review to know more about the quantum internet protocol stack. Okay, so I will go with one by one. From physical layers to the application layers, and let's look at the physical layer as I summarized in the previous slide. So physical layer job is that how do we generate and receive the qubits, right? We need quantum memory to store the qubits. We need fibers as a propagation medium, or free space as a propagation medium. These will be the job of the physical layer. And the link layer, it will be how do we generate the entanglement, for example, entanglement, and how do you transduce basically you have different types of qubits, whether it's superconducting or the photonic. Then you need to transduce or encode the information on that and put it on the wire, right, or non-wire, right? So that's very important. That's job of the link layer. And how do you couple the qubits to the quantum links, right? And here also comes the quantum error correction codes, right? So these are the functionality of the link layer. Now the question is, how do we generate entanglement, right? There are uh, different ways, but one approach that's widely popular is we can use the single source, right? And another is that how do we entangle the two different remote particles, that we will come later. Let's look at first the single source, right? So you pump, there is a laser source, and you pump the nonlinear crystal, and of course there are many criteria such as phase matching and the energy conservation, and then it will split the single photon at the pump wavelength, right? So this is the over omega p, which has higher energy, into two different photons, right? And if the criteria of phase matching condition and the energy conservation comes, it splits on a certain nonlinear crystal, such as BBO, or there is a PPNL crystal, and so on. It will generate the entangled photons, to one pair of photons. One we call it signal, another we call it idler, right? Through a single source, we can do that, right? If we take an example, so for example, let's say let's say take this state. If you want to generate it, what it says, signal is in horizontally polarized state. At the same time, what it is, idler will be vertical state. This is one type of entanglement state, right? Or another time, right? Another time, it's not at the same time. Another time, if the signal is in vertical state, polarized state, then the idler will be horizontally polarized state, right? So that's the superposition, and entanglement comes due to the correlation criteria. Right, so these, and they will be entangled. We need to test the entanglement, of course, through BSM measurement, Bell state measurement, or there are many, CHS criteria that one can do. But this is the way to generate entanglement, entanglement between two particles, which from the single source. How do we entangle two remote particles or qubits, right? And this is required for the qubits, the transmission to over long distance, right? So basically, I will explain the two different types of qubits in a quantum node. One is called communication qubit, which is used for generating entangled state, and another is called memory qubit, which is used for storing, sorry, the quantum state, right? Okay, so I will explain one simple protocol is called meet in the middle, right? How do you entangle two remote, the particles, right? So what it says basically is that first, you have one node 1 and node 2, and we want to entangle this, the one memory qubit to the another memory qubit. And for that, what basically this figure shows is that in brown circle, it is the communication qubit. Yellow circle represents the photons that will be transmitted, and blue is the memory qubit that we want to entangle, and gray is the photon emission, right? This thing, it's a very simple protocol. So as the name suggests, that meet in the middle. So transmitted this photons, basically they meet in the middle, and then we perform this Bell state measurement, the experiment, to ensure that they are really entangled, right? So what it is, this Bell state measurement. So you have Alice, which has the quantum state, rho A, and you have Bob, another node, which is with the state rho B. They are not entangled in the beginning. We don't know which state, even though you say, let's say one of the Bell states we want to generate, but we don't know which state Alice has and which state Bob have. We need to perform experiment, and if the experiment is successful, this Bell state measurement, then we will say that they are entangled. So basically, what we use the beam splitter to split to split and project on the polarization beam splitter, which have each one has the two detectors right here and there, and then basically you perform the coincidence count measurement, and then if you observe certain the dB coincidence count, then you say that okay, they are really entangled, right? Meaning that I will explain what are different purely entanglement state, Bell state, and then you are sure that these qubits on the memory, they can be entangled. Okay, so first, what is this protocol? It says that each node prepares an entangled state between its own communication qubit and a photon, right? It first prepares, because it has the same node, it can do it. And then second, the two nodes emit their photons simultaneously to meet each other and perform Bell state measurement at the midpoint, right? Exactly midpoint. This is also another, the difficulty. Exact midpoint it should be. Why? it will be clear. For the BSM, linear optics, and you can use the single photon detectors employed, and the success probability is 50% even in the ideal case. And if the BSM is successful, then this indicates that the communication qubits are basically at the two nodes are already formed the entangled state. And then once they are formed, then you can finally the state can be transferred from the from the communication qubit to the memory qubit for better storage, right? So this is the meet in the middle protocol. And similar to that, there are many different protocols. So I'm not sure. I forgot to bring my watch. This thing. What is the time now? Okay, so now it's 11:54. We have half an hour. That's good. Okay, let me make it. Yeah. Yeah, so sender receiver scheme is similar to meet in the middle protocol to entangle two remote particles, but what it says that sender receiver, right? Bell state measurement here is performed at the receiver, right? Instead of middle, right? Middle point has is tricky because it has to be exactly in the middle and has to be synchronized because both the photons from this one node sender and receiver needs to arrive at the same time, right? Then only you can ensure that these two photons are entangled if successful. BSM is successful, right? If there is a delay synchronization issue, then it won't, you will not make it sure that they are entangled. So to solve this problem, another protocol is proposed. Is called the sender receiver scheme. So here BSM is proposed at the receiver, and basically sender the transmits the photon, and then they perform the Bell state measurement at the receiver, and the results is communicated if it is successful or not to the sender, and then the quantum state is basically transferred to the memory for storage, right? This is, and then you call it the sender and receiver qubits are entangled, right? Another protocol is called midpoint source scheme, right? So now we can have another scheme. Because you see in the previous scheme, Bell state measurement is performed at the receiver, and then you wait, at the other end, right? Here, instead of that, you can have the source in the middle, and you transmit the communication. Sorry, these photons to the each to the they are entangled, and you transmit one to the node one and another to the node one, and then they perform the Bell state measurements at both the nodes. If the results are communicated over the classical channel, and then if they are successful, then we transfer the entangled state to the qubit, and basically then we call it they are entangled, right? So these are different the protocols. You can read the papers, and the source is given in the survey also. Yeah. So the network layer basically, as I told you, job is to entanglement, how to distribute the entanglement, right? So the question is, how can the Alice transmit the state of a qubit side to the Bob far away, right? So it requires, as I told you, it can do through the quantum teleportation, which also involves the entanglement swapping, right? And we will look at what are these, right? First, how do we swap the entanglement, right? So again, I already told you a little bit about the Bell state measurement. You need to perform the Bell state measurement to swap the entanglement from A to D, right? If A and B are entangled and C and D are entangled, we want to swap the entanglement from A to D, right? You can do it using the Bell state measurement. And here are the 4 different Bell state uh, the famous four-state bill state, which you can represent here as shown here. So basically what it says is that the particle 1 is in state 0 and particle 2 is in state 0, or particle 1, if particle 1 is in state 0, then particle 2 will be in state 1, right? There can be another state plus minus different superpositions, and then another interesting is like particle 0 in state 1 and particle 2 in state 1, sorry, particle 1 in state 0 and particle 1 in state 1, or if particle 1 is in state 1, then particle 0 is in state 0, meaning that if you measure at a detector that if you have generated this state, right? And if you measure at a detector that you receive first particle in state 0, and you know that this is the state generation, right? Then you already know that second particle must be in state 1 without measurement, right? So that's the key thing that you need to know. You can watch this YouTube for detailed description of the entanglement swapping. And here is the famous quantum teleportation protocol. It's it's the similar thing. So basically, what we want to do, we want to sorry, teleport, right, or transport quantum state psi from A to B, right? So we have to, okay, first we need to entangle, right, this with the psi, and to do that, to ensure that we do the Bell state measurement, right? After this successful result, then send the result, which is classical 2-bit information. You can read this paper for details. And this classical 2 bits information is shared to the node B, right? And the node B also performs some mathematical operations, right? And once they are they do the mathematical operations, again channel is ideal, nothing changes in between, right? Then you will be able, you will see that what you get here after the operation is the same state, quantum state psi, right? Only thing is that first you need to entangle this state A and B, they are entangled, and then we want to transmit quantum state from A to B, right? So yeah, please take a look at this paper, very old paper, theoretical paper, but some groups have already demonstrated this on a small scale, and people are trying to basically demonstrate over the using the chip or in the field, that's the thing. Now the repeaters, right? Repeater, before coming to the quantum repeater, what is a repeater? Repeater does the three things. It's regeneration, retiming, and re-amplification of the signals, right? Once the signals propagates from source to the destination over distances, it loses timing, it loses, I'm talking about the photons, but it can be another type of loss in another signal. We need to regenerate the signal, we need to retime so that you sample at the correct point, and also we need to re-amplify, right? This is the the third generation of the repeater. And and quantum repeater does not exist in the market, but on theoretically it has been proposed by many groups. So there have been proposal for different generation of repeaters, first generation, second generation, and the third generation, and basically how much capable they are with respect to the error correction, right, at the repeater. So basically that defines the quantum repeater. I will not go into the depth, but if you like, you can take a look at the many papers. Now the next is the quantum transport layer protocols, right? It is similar to the the classical transport layer protocols, right? So what is the job of classical transport? So how do you transmit the data? Basically ensuring the data transmission from source to destination, right? And in between, then we will have different switches, routers, etc., right? If it is long distance, right? So what is the one of the issues that arrives in network is the congestion, meaning that multiple packets or basically data chunks arrive at the router at the same time or even different times, but the memory of this the router is limited, right? So there will be congestion and there may be the packet drop, right? So how do we control that congestion, right? So so you need the feedback, right? If you look at the TCP protocol, it has the ECN, the explicit congestion control field, and basically it informs, hey, reduce the rate, from the source, right? And it has a sliding window protocol. Similar to that, we need to develop the quantum transport protocol. But if it's in the quantum domain, you cannot copy the quantum information, and so it's really tricky. Like, how do we do the feedback and all in the quantum channel, right? So and these intermediate routers basically tells the destination, hey, basically enables in this ECN flag and tells the receiver that, okay, memory is this much, 70% full. You need to inform that the transmitter that, hey, reduce your rate. by using this field, right? And then basically, if you have the loss of data packets, then you also need to retransmit those data packets, right? So if you cannot copy and hold in the quantum memory for a long time, how will you basically, retransmit those quantum data? That's a big question, and that we need to answer. But yes, theoretically, there have been proposals and simulation have been done, but yes, practical, demonstration have not been done yet. Now, application layer, right? This is the famous Alice Bob picture that you see here. That Alice wants to basically talk to Bob and our secure channel. Alice, says that, but they need to, need to first know whether they are really Alice and Bob, right? How can we be sure, right? In the quantum world, that's very difficult, right? Yeah, so quantum key distribution is one of the applications. I will explain a little bit another application, but let's look at this. Basically, in quantum mechanics, measurement causes disturbance, right? That's the fundamental thing, right? So we can use this disturbance to detect eavesdropping on a quantum channel. What does this say? This statement in classical, eavesdropper means someone unauthorized listening to your conversation, right? As a Eve, right? So in classical, there is no, you can simply, let's say, tap a fiber and leak some of the light, at some point, and then you assuming that you have all the decoding capabilities and all decrypting power, so basically they will be able to listen to your conversation, basically, right? How can we use the quantum key distribution to detect the eavesdropper? We will see. Okay, and this QKD presents this feature, and it leads to the provable secure key distribution. That's the one of the key driving application for the quantum communication, right? Okay. So let's remind about the quantum no cloning theorem. What it tells basically, an unknown quantum state cannot be cloned, right? Cannot be copied. Therefore, eavesdropper, when it tries to interrupt, right, the receiver may get to know, right? So single photon signals, right? If it taps, the if taps in the middle, the receiver will get to know after some iterations that, okay, then the bit error rate has quantum bit error rate has high, there must be some problem, right? Someone must be listening, someone is dropping the signals, right, at the end of the QKD process, right? But right, so what basically no cloning theorem is that Eve cannot take a copy of the signal and transmit another copy to the receiver, right? That is not possible, and that makes this QKD secure, right? So Bennett and Prasad, basically BB84 protocol, they actually published the paper in 1984 at one of the conference, in India, IC Bangalore, and and their idea was actually they were not able to publish their paper for some duration. No one was believing that this will ever work, right? So fortunately this was published, and then they published couple of it's papers similar, I mean same paper in other journals, and people started looking seriously on this protocol. So it has basically two things, right? We want to generate secure keys between Alice and Bob, right? So we can use quantum channel and classical channel. Eve has access to both quantum and classical channel. These are the assumption, and the channel is ideal, right? So no error due to the channel condition, right? All errors due to the Eve's, the Eve's presence, right? These are the assumptions, and for the quantum channel, what we do, we use non-orthogonal signals, right? For example, to represent, the bit 0, we can use either horizontally polarized photon or the 45-degree polarized photon, diagonal polarized, right? Or we can use bit 1 to represent bit 1. We can use either vertical polarization, polarized photons, or minus 45 degree, right? So they are non-orthogonal signals, right? Why it's needed? Because it's important for the security. And basically then the sender basically chooses this basis and then generates or encodes this bit 0 and 1 into this the quantum state. And at the receiver there is a random measurement, And receiver also uses this rectilinear basis or the diagonal anti-diagonal basis. Basically, if let's say L is transmitted 45 degree, meaning that the 45 will be 0, right? I'm not writing here the bits, but let's say 45. And above, the receiver used rectilinear basis, right? What will be the result? Uh, so this is tricky because this is not basically aligned in terms of polarization beam splitter. So what we do, it will pass to one of the arms, right? So what we'll do, either vertical or horizontal polarization you will get in one of the let's say in this channel. Basically it's two polarization beam splitter, 1 into 2, and each one, if it transmits it, if it gets transfers to this, you will get the horizontal. If it transfers to this, then you will get vertical polarized, and the probability is 50%, right? 50-50, half, right? What happens to this second one, this vertical polarized photon, you have the rectilinear which is perfectly aligned. So ideal case, you will get back the same polarized photon, right, at the one of the detectors. Let's say now 45 degree you want to transmit, right? And you have this basis aligned to this incoming photon polarization, right? So perfectly you will get the same output. Now I think you might have understood that what will be the result. For example, this one is it's a horizontal, and if you use the diagonal anti-diagonal, because we are using the random basis, right? We don't know what is incoming polarization of the photons, right? So you will get again 50% probability with the 45 degree and 50% probability for the minus 45 degree. You will get one of these two, right? Similarly, so basically these steps, if you follow along with some information reconciliation, then what will happen at the end, you will have, let's say, some bits, and over the classical channel, what is over the classical channel, you share basically basis that is that Bob has used to Alice, right? So basically so if they use the same basis, right, on each other, they share, right, measurement basis, right? So if the basis is matching, then they think that, okay, these bits generated must be correct, right? And after that, you also have to take some part of the keys, shifted key, and share to the for example, from Bob to Alice, to check whether that's the same string, right, they have got. And if that is also matching, then they take some remaining part of the key, the shifted key as a secure key, right, and store it for the encryption, right? So if there is an eavesdropper, obviously you will have much more bit error rate, higher bit error rate, and then you basically stop this process, and then you think that, okay, there must be something fishy going on. You can restart this process again, right? Yeah. So this is the thing. But in the reality, if there is a loss due to the channel or something, then yeah, it becomes a little bit tricky. So practical application is also tricky. So it's the ideal case. Okay, so what are the BB84 assumptions? The source emits perfect single photons, no multi photons. And then channel is noisy but lossless, no absorption in the channel, right? Detectors are perfect with the detection efficiency of 100%. Bases are aligned perfectly. Angle between different bases is, they are non-orthogonal, so 45 degree, basically, rectilinear and in the diagonal anti-diagonal basis, right? So these assumptions leads to the security proofs. That's information that's theoretically, theoretically information secure. So you can trust, you can say that it's secure, right? But due to these practical conditions, it leads to the security breach. For example, I explained to you, using a single photon source, you can generate signal and idler pair. That's entanglement. But similar to that, you can also emit with a single photon source also. One photon can be transmitted by attenuating the laser at the very low, very high level, and you can generate the single photons. But within a small time frame, you may be or may not be able to transmit a single photon, right? And when you encode, there can be the same, if it is entanglement based, there can be the repetition of the photons carrying the same information. So it's one of the attack is called photon splitting attack. So let's say the Eve copies, basically measures, right, one of the photons and let go another photon. Again, this is ideal case, right? It's not so easy now, and it has not been demonstrated, only on the paper, right? So this is the one drawback theoretically, and basically single photon is good, but multi-photon will be bad, right, for security point of view, and will have the it will be insecure communication, right? Another application that is interesting is the quantum key distribution, enabled quantum noise encryption. Let me look at again the time, and if there are questions, let me quickly go to this application, and then we will take some questions. Okay, so what it tells you that you can have the QKD to securely generate the keys between two remote parties, right? Now the question is, how can we use these keys for data encryption at high data rate? So you can use the classical advanced encryption standard, or there are the RSA, or there are many different classical encryption method. But the thing is, there are people believe that quantum computers will be coming soon, and that will break the security. So at the high data rate, ideal case would be take these QKD keys and use the one time pad encryption, meaning that you use the key and XOR with the data at the same rate, and you use the key only once and discard it. So that's the best. That's the information theoretic encryption that QKD along with encryption or one-time pad can provide. But QKD rate is typically kilobit per second, or the megabit per second, because of the source has limited entanglement and pair generation rate, and detector also has limited efficiency. Superconducting nanowires detectors are typically 80-85%, but yeah, it's still not 100%, right? So so we can use the quantum noise based encryption for using the these QKD keys and encrypting the data and transmit over the optical network, right? So it is proposed by Yuan in 2000, and subsequently Professor Prem Kumar's group has also demonstrated in the lab, and there are also Japanese group. They have done the demonstration in their lab, and I'm having a project with Professor Prem Kumar from Northwestern University on this, for using it for the advanced modulation. Okay, so let me give you this example. How can we use different modulation techniques for the quantum noise encryption? Let's say if you want to do intensity based, right? So you can use the PAM, multi-level, the pulse amplitude modulation technique. And so basically you have multiple levels of the intensity, right? But if you encode the information, if you have these levels much more than the then the number of photons present in that model, the signal, then what will it will have that the signal encoding will overlap each other, and you can use this the encryption technique, like with the key. A particular key can be used to select one of the bases. Basis is here the modulation intensity level, but here it can be the phase, right? Here it's a phase based, and here it's QAM, right? So without that key, you will not be able to, let's say this is you are receiving, right? So actual phase this of this signal may be lying around this, right? So you will not be able to know whether it's this one or this one or this one, right? So basically it hides the information in the noise. That's the the concept, right? And it also involves in the improves the security. Okay, so there is a question we will take, and so basically what it tells is that quantum noise is a stream cipher, as the name says, it's a stream cipher bit by bit, not the block cipher. basically if you have the number of bases, number of bases, you divide whether it's intensity or the phase into multiple, the basis points. And if the number of bases is more, meaning that this distance is very close, right? And if it is more than the square root of the number of photons per bit, then you can ensure that the information is hidden under the noise. And without the key, basically key is used to choose the basis, which phase, which intensity to use for encoding a particular bit, right? Then you will be able to, you know, improve the security on a much more higher level. Of course, it's not 100% as one-time pad, but yes, at this high data rate, it can be used, and still there is no breach have been demonstrated. So, and they have already demonstrated the phase-based, I mean, the Prem Kumar's group, the phase-based quantum noise-based encryption and decryption. And as I told you, Japanese group have done the intensity-based, and we will do with the some advanced modulation. Okay. So that's the thing. And at the end, I would like to say there are many quantum networking challenges. Like how do you achieve the transport in quantum networks without destroying qubits? How do you switch and route in quantum networks without destroying, qubits? How do you place a control plane? Control plane, you need to take the decisions for routing in quantum networks, right? How do you build that? How do we manage the quantum networks? How do you monitor the performance of quantum networks? All sorts of challenges are there apart from the hardware, from the software and implementation, right? And yeah, so we need to develop the quantum devices, and then no one is going to overhaul the today's classical fiber network infrastructure. So the question is whether we can use the classical network and in coexistence with the quantum, the signal transmission. Yes, the coexistence is one of the hot topic that people are trying to transmit the quantum signal and the classical signal on the same fiber, of course, either on the same channel in the time division multiplexed manner, which we also have demonstrated, and or in the wavelength division manner, meaning that on different channels. So due to the scattering and other issues, you will be dealing with the such noises, and signals get affected, right? So yes, so at IIT Roorkee, we have digital art communication sensing, the MTech program where I have been involved, and now currently I'm on leave at TU Eindhoven. And we have many PhD positions in the group, many this funded projects we have. And actually 2 days ago we have another grant, web of grant we received. I received actually with Professor Prem Kumar from US. It's prestigious, and he will be in Roorkee regularly. And we provide internships. We have projects you can look at, and you can contact me anytime. If you have now the questions, you can ask me, and I will be happy to answer. Let me look at the chat. With that, yeah, let me think. Okay. Do we have any specific questions or formulas for QKD, Alice and Bob communication? Of course, as you said, you can. I can tell you the reference books, and the name. It's a quantum communication. I'm just forgetting the author name. I can take a look, and I will share the PDF of the slides, and then in that email, maybe to Rajenderji, I will send the link of these books. And there are actually on YouTube actually, and also Coursera, there are very good lectures actually that you can refer. The software, okay, I believe this QKD and software key distribution is used mostly in quantum secured microgates. Okay, so that's one suggestion. So of course, microgate and other type of the networks you can use. What are the application in electrical engineering? Okay, electrical engineering, I'm not sure exactly what you are referring to. So electric, the physicist that got the Nobel Prize, actually that was the tunneling in the electrical circuit actually. So yeah, some of the maybe at the end I will have more references. I have not talked to you, in fact, my key, like the projects. Let me see if I have the references. But definitely I will send you. Okay, and the YouTube videos links are already there. And yeah, so power distribution. This is already one suggestions in electrical engineering. Quantum machine learning and QKD, how they are linked with LLM tuning. I'm not working with the quantum machine learning, but my colleague, Professor Bodhi Prata, he has started a new course on quantum machine learning. Yeah, so you can like the way you do the typical machine learning. So instead of that, how do you use the quantum state and its properties to to instead of stochastic SGD, right? Optimize, and you have to do the quantum, you have to deal with the quantum signals, right? Quantum state, and how do you optimize it? How do you minimize the error? So yeah, but I'm not an expert in quantum machine learning, but definitely it's a very hot area, and you can also publish papers easily, actually. Yeah. Can we use quantum for random key generation? Yes, of course. There are many techniques for example, quantum noise, right? For generating random key, right? Random, okay, key generation. You mean random RNG, right? Random number generator, right? So yes, there are Professor, if I recall, also Professor. What is name in India, Delhi? He's very famous in India. So I just forgot his name. So he's doing this. He had okay, I'm just not recalling. Yes, but it's many people have already RNG with for the quantum, right? And QML. Okay, we will be having one, the quantum computing and quantum computing algorithms and communication. This course for industrial people or non-industrial people, offered by I'm the coordinator, and with me there are I'm in communication. There are professors from computing. QML, I already told you his name. He will be there. So four of us will be doing this course, and you can register. Actually, its registration is still open, so you can take a look at the CEC website, continuing education center, and you can find this quantum computing course offered by us. Yeah, Ajay Ghatak, he was at IIT. I met him, and he's classical, but now his talk was very good, actually, wonderful. And but what I was referring is not Ajay Ghatak. I was referring to another professor. Yeah, Anirban Pathak, Professor Anirban Pathak. So he's doing good work in cryptography. Yeah. Is there anything for undergraduate students? Of course, quantum communication course. Let me quickly tell you the quantum. I'm sure you are able to see my this thing, but let me quickly find it, and I will do know itself. Where are the books? I was reading this book a couple of years ago. Professor David Miller course also I have taken from Stanford. So this was very good. If you type in Google, you will get it. And this Nielsen and Chong book is the like for information system, but you must read this book. This is very interesting and very good book for quantum communication. In particular, I can tell you now. I have the PDF also. You can also easily download. Let me open this and tell you the author's name. Yeah, Quantum Communication by. I'm writing in the chat. Quantum. This is a good book. Quantum Communication. There are not many books on communication, but yes, this book is good. Gianfranco Laro. Yeah. So I have written in the chat. Apart from that, of course, there are on YouTube and yeah. So if there is nothing more, we will stop. And if you have any, maybe one or two last questions, you can also ask, unmute if it is possible. And yeah. we can stop this session. Yeah.
Thank you, sir. Thank you for this session. And I think all participants are interestingly listening this lecture because it is a versatile. You're covering 3 or 4 the main recent topics, the application topics at which you can use this quantum. So thank you, sir,
Yeah.
for
Thank you.
taking.
Thank you. Thank you so much, Rajendra ji, again for inviting me for this talk. And thank you all the participants
It's
for
our
listening.
pleasure that it's also a
Yeah.
time delay at your side.
No,
And
no problem. It's fine. It's from my side. It's okay. So yeah, I was sick a little bit, but I think except little bit of interruption, everything went well. So thank you so much.
yes, everything is okay. So thank you, sir.
Yeah. Bye bye.
Yes, bye.